Welcome to Honors Chemistry. We're looking at our essential question on how do ions form. And the first thing that we're looking at for this particular lecture is where we find metals, metalloids, and nonmetals. And so we can see that our metals are located mostly here on the left-hand side of the periodic table and down here in the lanthanoids and actinoids. And then we see that we have metalloids that kind of separate the metals from the nonmetals, except for we have hydrogen way over here on the left in the top corner. And so it's important to recognize what is a metal and what is a nonmetal as we start talking about ion formation, because metals and nonmetals behave differently in forming ions. And so this is also going to help us later on if we know how to identify these things or where they're located on the periodic table. Is going to help us identify the types of compounds that we're looking at when we see a chemical formula. We're going to know whether it's a molecule, a formula unit, and that type of thing. So we can definitely, we're definitely going to need to know how to determine whether a substance is a metal or a nonmetal. So make sure you label those in there. Then on this, I had you list some properties of metals and nonmetals. We see metals form cations and nonmetals form anions. We're going to go over those two terms today. Metals have a luster or a shine, whereas nonmetals do not. Metals are good conductors of heat and electricity. Nonmetals are poor conductors. Metals can be shaped, whereas nonmetals are brittle. They would break real easily. Metals have high melting points, so it's going to take quite a bit of energy to get them to change from the solid state to the liquid state, whereas nonmetals have low melting points. We notice that most metals are solid at room temperature, whereas a lot of our nonmetals are liquids or gases at room temperature. And so there we have some comparisons of our properties. So list those in your handy dandy notebook and that will be great. So we're going to go ahead and start with ions, and our job today is to define ion, define cation, and define anion. And so ion is just a general term for an atom with a charge. And so if we look at what are ions, ions are atoms that contain an unequal number of protons and electrons, which result in an overall positive or negative charge. So if we summarize that real quick, ions are atoms with a charge. All right, now that charge is going to be driven by the fact that it has an unequal number of protons and electrons. Remember, we've talked about neutral charge atoms, and they have equal number of protons and electrons, but ions are atoms with a charge. They are not neutral. So they're going to have an unequal number of protons and electrons. And so that is just a generic term, ion, atom with a charge. Now we can get a lot more specific with our terms when we say cation. So we ask to define cation. Now we are being specific about an atom with a positive charge. Now, how does an atom get a positive charge? Well, it has to have more protons than it does electrons. So it has more positively charged protons than it does negatively charged electrons. And so it has an overall positive charge. We call these a cation. So cations can also, I can remember this by it has a T, and you can think of that as a plus sign, right? Cation. So that's another way. So, and then also we know that cats, they have pause. So we can say that cations are positive, positive. All right, sorry for that. That was actually terrible. Okay, anyway, just a way to remember it. Then we go to anions, and anions are, again, another type of ion, and it's a lot more specific than the generic term ion. An anion is a negative ion, and so I look at it as a negative ion, a negative ion. Anions are atoms that have a negative charge. And how do atoms get a negative charge? Well, they have to have more negatively charged electrons than they do positively charged protons. And so that's our condition for an anion. And here I have a graphic that shows us the same condition. So we have a cation. Here we see that it has 5 protons, 3 electrons. So actually this would end up with a 2+ charge. Here we see 3 protons, 5 electrons. This would actually end up with a 2- charge. All right, and so why? Because the cation has 2 more protons than it does electrons, and the anion has 2 more electrons than it does protons. And so we can see those things. Why we get positive ions called cations, and why we get negative charge ions called anions. And we see the conditions for meeting both of those. So those are important terms to know. Those terms are used very, very often, and you're expected to know what they mean when I say those things. So not difficult terms to probably pick up, but definitely very important. All right, so we now move into a little bit closer to our objective here, and we're looking at our question is, what type of elements tend to form cations? So cations, we can see, are metals lose electrons to form positive ions, leaving complete octet is not a bad term, but it's not specific enough for me. So metals lose electrons to form positive ions, leaving a noble gas electron configuration in the next lowest energy level. And so what do we know about noble gases? They are all the elements in group 8A, as listed right here on this periodic table: helium, neon, argon, krypton, xenon, radon. And so we see all of those. And so those are our noble gases. And what we notice about our noble gases is they have these very specific configurations. So I'm showing these here. And we see helium has an S2, whereas all of the other have S2P6, S2P6, S2P6 in their highest energy levels. And we can see their highest energy levels here. That's 1, that's 2, this one is 3, and this one is 4. And so we can see that in those, for the most part, we get an octet, 8 electrons. And so what I scratched out here says, let me see if I can go back to it. Whoop, there we go. What I scratched out is giving it a complete octet, and the octet meaning 8 valence electrons. Well, that's not specific enough, because helium, as you see, does not have 8 valence electrons. So in fact, helium has only 2. And so we're going to talk about that here in just a second. All right, but nonetheless, they lose electrons to form this noble gas electron configuration. So how are cations formed? By losing electrons to form a noble gas electron configuration. Now it asks us 3 questions, and these can be answered fairly quickly with a single explanation. So we're going to go through this, but got to pay attention to this part very closely, because this is a big deal right here. So which main group elements tend to form 1+ cations? Same question for 2+ cations. Same question for 3+ cations. So things that I want you to notice before I get into this is that on this periodic table that I have here, we have written dot structures for each element. Now these dot structures, as the title of this periodic table says these dot structures represent valence electrons. So what we notice is that 1 dot would represent 1 valence electron, 2 dots represents 2 valence electrons, 3 dots, 3 valence electrons, so on and so forth. So other things that we want to notice is how these dot structures are written. So we notice that if we go to group 1, and it doesn't matter where we start on drawing dots, but they have a single dot. And then we go to group 2, and we notice, like for magnesium, we notice that there's a dot on 2 sides of the symbol. And that is proper for drawing dot structure. So when we draw a dot structure for magnesium, we would not want to draw two dots on the same side of the symbol. So when we draw dot structures, they do represent the number of valence electrons. And we should know that magnesium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. I wish my handwriting was a little better there. But maybe I'll change it. 3s2. There we go. And we notice once again, highest energy level. Oh, why did I say 3p6? I'm sorry. That's not right. I got carried away. It's 3s2. Stops at 3s2. Sorry about that. I do know what I'm doing. 3s2. There we go. So our highest energy level is energy level 3. And then this is 3s2. We know this is S and that's S2. So we see that magnesium has 2 valence electrons. In the highest energy level in the configuration, there are 2 electrons. So those electrons have to be expressed with dot structures. We place 1 dot around the symbol until they're forced to pair. All right, similar to what we saw in Hund's rule with orbital diagrams, but this is something a little bit different because this is dot structures, but nonetheless, when we symbolize these, we put 1 dot around the symbol until they're forced to pair. So notice when we get to boron in group 3A, boron has 3 valence electrons. We added to that, this would be 3p1, so 3 valence electrons. And so we notice that there's a dot on 3 sides of the symbol. We go to carbon, we see that it has 4 dots, so it has 4 valence electrons. Now notice when we get to nitrogen, now there was a forced pairing. So we see the fifth electron is now forced to pair with one of the others. And so that would be a good drawing. Go to oxygen, it's the same thing. They did 1 on each side and then 2 were forced to pair. Fluorine, same thing, 1 on each side. 3 of those were forced to pair. And then neon, 1 on each side. And then all 4 sides were forced to pair, as it has the full octet or the full 8 electrons in this valence shell. As we see with most noble gases, the only one that we have an exception with is helium. Okay, so that gives us some perspective here as to the number of valence electrons in each of these groups. Now we're going to be talking about these representative groups, and I had you the other day to write 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A on your periodic table. And so these are representative elements. And so what we're going to do, or we can call them main group elements, what we're going to do is see if we can find some relationship between the group and the number of valence electrons. And so if we go to group 1A, what we notice is each of those elements, hydrogen all the way through cesium, have only 1 dot, meaning that each of those have only 1 valence electron. If we wrote the electron configuration for every one of those, we would notice, sure enough, they have 1 valence electron. So group 1A has 1 valence electron. Each element in group 1A has 1 valence electron. Each element in group 2A, what is this? Has 2 valence electrons. So group 1A has 1 valence electron. Group 2A has 2 valence electrons. Group 3A has, wow, all of those have 3 valence electrons. And those in group 4A have 4 valence electrons. And those in group 5A have 5 valence electrons. And those in group 6A have 6 valence electrons. And those in group 7A have 7 valence electrons. And those in group 8A have 8 valence electrons, with the exception of helium. All right, and so your question may be, well, why is helium the exception here? Why does helium only have 2 valence electrons? Shouldn't it be in group 2A? Well, maybe, maybe not. Let's think about helium for a quick second. So we see helium. We know helium is in in energy level 1. And energy level 1 only has an s sublevel. And that s sublevel can hold only 2 electrons. So helium has a full valence shell with 2 electrons. All right, so because it has 2 electrons in its valence shell, and it can only hold 2. So it's a full valence shell. If we go to the other noble gases, they also can hold 2 electrons in their s sublevel, but they have an additional p sublevel, which holds an additional 6 electrons. And you will notice that the s sublevel, which can hold 2, has 2 electrons, and the p sublevel, which can hold 6 electrons, has 6 electrons in it. And so we see that it has a total of 8 electrons. All right, and so if it can hold 8 and it has 8, well, then it also has a full valence shell. All right, and so helium is placed over here with noble gases. Let me see if I can get this periodic table to show up. All right, helium is placed over here with these noble gases because it has a full valence shell just like the other noble gases. And so it behaves very similar to the other noble gases. Also, you might notice, let me go back over here a little bit. You might notice that helium, they have the 2 dots paired together. And I believe this is the exception to our dot structure rule where we have to show a dot on each side. I believe the only reason why they're showing those 2 together on one side is because it only holds 2 in its valence shell. So there's no way it can hold more than that anyway. So they just put those 2 on the one side. Helium would be the only exception to pairing up before it's forced to pair going all the way around the symbol. So that would be the only exception. So, but helium is over here in group 8A with 2 valence electrons because it has a full valence shell just like the others. But its valence shell is full only when only with 2 valence electrons. All of the others are going to require 8. So it is also another reason, because its valence shell is full, it behaves just like the other noble gases. It would not behave like group 2A elements, which have only 2 valence electrons, but their valence shell is not full. All right, they can hold more. And so they have different properties based on its ability to hold more valence electrons or whether or not its valence shell is full. All right, so we went through all of that to now answer our question. So we know about metals. Metals, we know where they're located. We know that they lose electrons to form a positive ion, leaving a noble gas electron configuration. So here is an example of sodium, and we see sodium, here's the atom, has the same number of protons and electrons. So we see this has 11, of course you can't see this, but it's 11 protons because it's sodium. And it also has 11 electrons, one of the electrons out here in its outer shell. How do we know? Because it has 1 valence electron. There it is in energy level 3s. So when sodium loses this electron, now this whole energy level goes away, right? It's gone. And so the next energy level that we have left contains 8 electrons and has a noble gas configuration. Look, a full S and P sublevel in its highest energy level. Therefore, it has a noble gas electron configuration. Actually, this has the same electron configuration as neon. So if we were to look at the configuration of neon, it is the exact same. So it has a noble gas electron configuration. Now, since it only lost 1 electron, then we now know it has a 1+ charge. All right, has a 1 plus charge. So it had one valence electron to lose to get to that noble gas electron configuration. It did, and now it has a 1 plus charge. And it has the noble gas configuration of neon. So we can look at some others. And if we look at aluminum, for instance, we find aluminum on our periodic table. We notice, sure enough, it has 3 valence electrons. We also notice that it's a metal, and metals tend to lose electrons. So I'm going to show you the configuration of aluminum. And sure enough, on our configuration, see if I can get those others to show up. There we go. Sure enough, on our configuration, we see that it has 2 plus 1 valence electrons. So it has 3, just like the picture showed. Now, what happens if we just erase one of those electrons, or one of those electrons gets removed? Do we have a noble gas electron configuration? No. We have, in the highest energy level, just S2. Remember, in the noble gas configuration, with the exception of helium, the S and the P sublevels are full, meaning they have 2 in the S and 6 in the P. So we do not have a noble gas electron configuration just by removing 1 electron. So we have to remove all of the valence electrons. And when we do, we remove all 3 valence electrons, now we have the noble gas configuration of neon. And there it is, 1s2, 2s2, 2p6. Notice it has 8 valence electrons in its outer shell. But since it lost 3 electrons, it must have a 3 plus charge, all right? Because now aluminum has 13 protons, but it only has 10 electrons. That gives it a 3 plus charge. See that? Because it has 3 more protons than it does electrons. And that's where we're getting the 3 plus charge. It has 3 valence electrons. It has to lose, well, first of all, aluminum's in group 3A. It's a metal. It tends to lose electrons. It has 3 valence electrons. It loses those 3 electrons, obtains a noble gas electron configuration, and after that, it has 3 more protons than it does electrons. So it gives it a total charge of 3 plus. If we look at magnesium, we see magnesium, sure enough, there in group 2A, has 2 valence electrons. We notice that magnesium is a metal, and metals tend to lose electrons to form a cation. But they don't just lose an electron, it loses enough electrons to obtain a what? Noble gas electron configuration in the next lowest energy level. So if we go to magnesium, we see that its next lowest energy level is energy level 2. If we remove these 2 electrons in the highest energy level, we're left with a noble gas electron configuration. And it's, again, the same configuration as neon. But this time, magnesium lost 2 electrons. So if it lost 2 electrons, that means it has, let's go ahead and let's do this by the numbers. It has 12 protons, but now it has 10 electrons. That is giving it a charge of 2 plus. So this is a 2 plus charge. So now we go to sodium, and we kind of worked with sodium already, so I'm going to go through this fairly quickly. But sodium is a metal, it has 1 valence electron, it loses its 1 valence electron, and so now we see that it has 11 protons and 10 electrons and has a charge of 1 plus. So we see that. So now we have our charges. Now also notice something very interesting here. Aluminum was in group 3 and it forms a 3 plus cation. Magnesium is in group 2 and forms a 2 plus cation. So watch this. So we got group 3A, group 2A, group 1A. So we notice group 1A has one valence electron, but it forms a 1 plus cation because it's going to lose that one valence electron to obtain its noble gas electron configuration. Group 2A has a 2 plus charge. It had two valence electrons. It loses both of its two valence electrons to obtain the noble gas electron configuration and ends up with a 2 plus charge. Group 3A has three valence electrons. It loses those three valence electrons to obtain a noble gas electron configuration and ends up with three less electrons than protons for a 3 plus charge. So can we make some generalizations here? Absolutely. So we can see even from this chart here that group 1A, they are going to form a 1 plus charge, and then 2A forms a 2 plus charge, and then 3A, they form a 3 plus charge. Any elements in those groups will form those charges. Now, I want you to update your periodic table with charges above where I told you to put the 1A values or the values, the A values the other day. So notice above 1A, we have a 1 plus charge. Above 2A, we have a 2 plus charge. And above 3A, a 3 plus charge. So if I asked you, what charge does barium form? You would know it forms a 2 plus charge. How do we know that? Because it has two valence electrons. It's a metal, and it will lose those two valence electrons to obtain a noble gas configuration of xenon. You see that? And so it would end up forming a 2 plus cation. So we can find that real quick. If I ask you what charge does cesium form, we can go to cesium. We can see, I went right next to barium. Let's go to potassium. Potassium, what charge does potassium form? We know it's going to form a 1 plus charge because it has one valence electron. It's a metal. It's going to lose that one valence electron to obtain a noble gas electron configuration of argon. And it's just really that simple. And so if you have those charges indicated above the group numbers for these representative elements, those ones that have an A indicator, that's going to be real easy to tell. Group 1A has one valence electron, 2A, two valence electrons, 3A, three valence electrons. Group 1A has a 1 plus charge, 2A has a 2 plus charge, and group 3A has a 3 plus charge. And so that's really, really easy to work with. Now we move into the next part, and that is going to be looking at how to write our equations. So we want to show an equation for the ionization of sodium. So sodium is going to end up losing an electron. So what we're going to do is we're going to show sodium as an atom. All right, we're not going to show this from an energetic standpoint, but we're going to show sodium as an atom. And then there's something happens, energy is inserted, but so the electron is ejected, and we end up where the electron is transferred via an ionic transfer to an ionic compound, whatever. We're just showing this with an arrow. Sodium, reaction arrow, and we're showing sodium with a 1 plus charge. Now, how does this get this 1 plus charge? Well, it lost one electron. So now this one electron being separated from the sodium ion, we can account for why that has a 1 plus charge. Also, I'd like for you to draw a dot structure for the same thing. What we notice here is we're showing sodium with the 1 dot above it. So it's showing it has one valence electron. Here's its electron configuration. Here's the reaction arrow. Now, when we draw the dot structure for an ion, let me be more specific. When we draw the dot structure for a cation, no dots are shown, and it indicates that the electrons are lost. Now, notice there's no dots on this cation, but we do have to indicate the charge. All right, we do have to indicate the charge. So there was one electron. Now that electron is gone, and sodium has a 1 plus charge. Notice the electron configuration. We do not see that 3s electron there anymore. Where is it? It's over here. All right, it's gone. It's being transferred. It's, as far as sodium is concerned, it's lost. We'll talk about details later on. So notice here we're putting a 1, indicates the number of electrons that is lost to achieve the noble gas configuration. So we see that sodium 1 plus does have a noble gas electron configuration. And so that's how we would indicate that substance right there. Now we're going to move on to anions. Now, how do anions form? So what type of elements tend to form anions? Anions are formed by nonmetals. Nonmetals tend to do what? Gain electrons. Now, when something gains an electron, remember electrons are negative. It's gaining something negative, so it's going to form a negative charge. And so anions are nonmetals, or are formed by nonmetals, which gain electrons to form negative ions and achieve a noble gas electron configuration in its valence shell. All right, so again, it's going to achieve a noble gas electron configuration in its valence shell. So how are they formed? By gaining electrons to achieve a noble gas electron configuration. Now, which main group elements tend to form a 3 minus, a 2 minus, and a 1 minus charge, and why? So let's take a look at this. So we're going to look at this from a little bit different way than we did cations, because it's a little bit easier to using these dot structures for at least the addition of electrons. So we notice that we have our representative elements group. Here was group 1A, 2A, 3A. Those are mostly metals. Now we're looking over here. Let me put it with a red line. All these yellow right here, and we're going to leave carbon out for right now. All of these over here are our nonmetals. Now, noble gases, they're not going to form ions because they already have a noble gas electron configuration. So we're not going to really consider group 8 here because they have a noble gas electron configuration. So how do we get our charges, is what we're asked in the prompt. So we see that nitrogen, didn't like my line there, that nitrogen, all right, has 5 valence electrons. Now it wants to have a noble gas electron configuration. It wants its S and P sublevel to be full. Right now it has 2 electrons in its S sublevel and 3 electrons in its P sublevel, for a total of 5. This is where we're getting 5. 2 in the S, 3 in the P. Now, what's happening is, I'm going to use a different color here. We're going to see that nitrogen needs to gain 1, 2, 3 electrons to have the same electron configuration as neon. All right, so here's nitrogen's electron configuration: 1s2, 2s2, 2p3. But when it gains 3 electrons, so we're going to change this 3 because it's going to gain 3. That means it would be 6. It's going to have the same electron configuration as neon. All right, so this would be nitrogen 3 minus. All right, so why? Because it gained 3 electrons to obtain a noble gas electron configuration. So this is going to be the same thing for all elements in group 5A. Why? Because they all have 5 valence electrons. Excuse me, let me say this again. This is going to be true for all nonmetals in group 5A. Why? Because they have 5 valence electrons, and they would need to gain 3 to get to 8. So if we notice the same thing for phosphorus, 1, 2, 3, and it would have the same electron configuration as argon after gaining 3 electrons. So it would have a noble gas configuration of argon after gaining 3 electrons. And so we can see that very easily. So above group 5A, we can definitely write a 3 minus, and I showed you that on that periodic table earlier. But all group 5A nonmetals will form a 3 minus cation. So if I am just looking at my periodic table and I say, what charge will phosphorus form as an ion? We're going to say that it is 3 minus. And actually what we call phosphorus as an ion is phosphide. All right, and we call nitrogen as an ion nitride. We end up adding an IDE ending to the name of anions when they form ions. So it's no longer nitrogen, it's nitride. It's no longer phosphorus, it's phosphide. All right, and so when we go to group 6A, it's a very similar thing, except for group 6A. How many valence electrons does it have? That's right, 6. Wow, this is very difficult. And so it needs to gain 2 electrons to obtain the noble gas electron configuration. And when it gains its 2 electrons to get the noble gas configuration, that means it has 2 more electrons than it does protons, so it will form a 2 minus charge. And we call oxygen as an ion oxide. And we would do the same thing for sulfur. It would gain 2, and it would form a 2 minus charge, and we would call that sulfide. And selenium would also gain 2 to obtain the noble gas configuration of krypton, and we would call that selenide. But all of these gain 2 electrons to get to their respective noble gas configurations, and when they do, they obtain a 2 minus charge. Now we go to group 7A, and we know group 7A has 7 valence electrons. So fluorine, for instance, only needs to gain 1 electron to have the same electron noble gas configuration as neon. So when it gains only 1 electron to have that same configuration, we know its charge is going to be 1 minus. And we call that fluoride. And chlorine is going to gain 1, and we call that chloride, Cl1 minus. Bromide, iodide. And so all of those would have a 1 minus charge, all right, because they're in group 7. So you can go above group 5A, 6A, and 7A, and you can write above 5A 3 minus, above 6A 2 minus, and above 7A 1 minus. And that would help you determine the charge of a specific element by group, or what charge a specific element will form when it ionizes by looking at the group. All right, and all of that's driven by the number of valence electrons that each atom has. So remember, each group of group 1A through 7A, or group 1A through 8A, they have the same number of valence electrons in each group. Group 1A has 1 valence electron all the way to group 8A, which has 8 valence electrons, with the exception of helium. Helium was the only one that was different, and it was only there because its valence shell is full, just like the other noble gases. All right, and so if we look at a Bohr model of chlorine forming chloride, we can see that here we have chlorine. Here's its valence electron, 3s2, 3p5. It's in group 7, has 7 valence electrons. Here it gains an electron to get to 3p6, has the same electron configuration as argon, and so this now becomes chloride, Cl1 minus. And so that's all we need to really show there. Now we're writing an equation for the ionization of chlorine. Now this is a little bit different than what we see for cations. Remember, I'm going to take us back up. For cations, we're showing the electron on the right side of the arrow, or on the product side. We're showing that sodium ion lost this electron. But what are we doing when we have anions? They gain electrons. We're adding an electron. So we're showing an electron on the left side of the arrow. And because chlorine is in group 7A, it has 7 valence electrons, it's only going to gain 1 electron, and then it's going to form the chloride ion with a 1 minus charge. And we can see that that's even consistent with what we wrote on our periodic table. And so we can see This is an equation for the ionization of chlorine. You see, chlorine plus 1 electron gives us Cl1 minus, and it will have a noble gas electron configuration. Now we can also do this with the dot structure equation for the ionization of chlorine. Here we have chlorine. We notice that chlorine has 7 valence electrons. Now, how do we know that? We know that from the electron configuration. We can see that 3s2, 3p5, a total of 2 plus 5 electrons in its highest energy level. Also, we could go to our periodic table and see that it's in group 7a. So we should know there's group 7a elements have 7 valence electrons. We now know we're going to indicate that we are adding 1 electron, and this 1 is indicating the number of electrons. We could have, if we were talking about sulfur, we would want to put a 2 there because sulfur has 6 valence electrons, so we want to have to add 2 electrons to obtain the noble gas electron configuration. But for chlorine, it only needs 1. And so we add the 1 electron, and then on the reaction arrow for a dot structure, what we have to do for dot structures for anions and anions only. Notice we didn't put our cation in a bracket, but for anions we put a bracket, and then we show the additional electrons. So here it was 7, here it was 8, and so outside of the bracket we indicate the charge. So we notice it went from 3s2 3p5 to 3s2 3p6. It did obtain its noble gas electron configuration with the 1 additional electron. So there are some differences in how we express our dot structure equations for cations and anions. Here they are in your notes. You should have those listed, and then you're going to be doing this in your daily work as well. So make sure you're paying attention to these expressions as you're doing your daily work, and I think you're going to come out golden. All right, once again, on your periodic table, make sure you update your periodic table so that it indicates groups 1A through 8A, and then also over group 1A indicate a 1 plus charge, over 2A a 2 plus charge, over 3A a 3 plus charge, over 5A a 3 minus charge, over 6A a 2 minus charge, and over 7A a 1 minus charge. We should understand why those charges occur based on the number of valence electrons they have, and based on whether we're talking about a metal, which tends to lose electrons to form a noble gas electron configuration, or whether we're talking about a non-metal, which tends to gain electrons to obtain the noble gas electron configuration. So for this lecture, we are over. Thank you for watching. Please like and subscribe.